You know that the method of indicators is very useful for finding expectations of random counts. That same representation of a random count as a sum of indicators is a good way to find the variance of the random count. And for that, we're going to need the variances of the indicators, which we already know, but also the covariance of two indicators. So let's find the covariance of two indicators. Now, indicators are very simple random variables, values zeros and ones, so we should be able to just work from either definition or the representation of covariance as expected product minus product of expectations. Let's just work on that. So we just apply the formula that I just said that says that you find the expected product and you subtract off the product of the expectations. Now, which of these bits do we know? We certainly know that the expectation of an indicator is the probability of the event that it indicates. So that second piece we know. And we now have to look at the product, the indicator of A times the indicator of B. This is a random variable. And what are its values? Values are either 0, 1. And it's a function of indicator of A and indicator of B. Both of those have values zeros and ones. When is the product equal to 1? When both are equal to 1. So the product is equal to 1 if and only if both are equal to 1, which means that the product is equal to 1 if and only if the intersection has happened. And so what we are noticing is that the product of two indicators is itself an indicator. It is the indicator of the intersection of the two events. It's a good idea to just take a look at the notation here. That intersection AB is not a product, it's an intersection, as it has been since early in the class. But indicator of A times indicator of B is a product of two functions. Well, if that's the case, if the product of the indicators is itself an indicator, then we can easily write down its expectation is the probability of the event that it indicates. And hence, the covariance of the two indicators is the chance of the intersection minus the product of the chances, and that is following from here. Great, we have a calculation. But now if you look at that, what you see is on the right-hand side, you have the chance of the intersection. What you're subtracting off is what the chance would have been if the two events were independent. And so now clearly this is picking up some way of measuring the amount of dependence between the events A and B. So let's note, if A and B are independent, then the chance of the intersection is equal to the product of the unconditional chances. So the indicators are uncorrelated. So this is a special case of a result that you've seen, which says that if any two random variables x and y are independent, then they are uncorrelated. In our situation, this leads to a conclusion about events that are not independent. If A and B are not independent, then our old multiplication rule says this. So now let's look at what happens if the covariance of the two indicators is positive. By how we are computing covariance, it must be true that the chance of the intersection is greater than the product of the chances. And the chance of the intersection is what we just wrote down here. And the conclusion from that is that if the covariance of two indicators is positive, then the chance of one of the events given the other is bigger than the unconditional chance. So if the covariance is positive, then my telling you that A has happened increases what you think is the probability of B. And so given that A has happened, B is more likely to occur than it was without that information. And this relation has a direction. This is called positive association. And analogously, if the covariance of the indicators was negative, then telling you that A has happened would reduce your chance that B is going to happen, and that would be called negative association. So in this sense, the covariance is measuring the kind of dependence that these two events have.